Okay, so I want to do 1.4, number 4. Let's see, somehow I think I can get page lines on here, but I don't remember how, so give me 1 second. Probably should have done this first. There we go. Rule lines. No, that is not what I want. Maybe a little bit bigger. Too big. There we go. All right. So this is what we're trying to prove. It's a set theory proof. It has an if and then. So we're going to start by assuming the if part. Assume that Z is a subset of X. Okay, and remember what that means is, therefore, we can say if I pick some element A that's in Z, then that element A is going to be in X. Right? And that's because of the definition of subset. Right? Okay, so the rest of the proof, now the way I'm going to refer to this, I'll call this right here just like big A and this big B, because if I just read them out loud, X intersect Y union Z, you could call that either one. And I don't want to keep referring to all the parentheses. So we're trying to prove set A equals set B. The way to do that is, remember, we have a two-step proof. A has to be a subset of B. B has to be a subset of A. So this is going to be part 1. This is going to be part 2. Okay? So part 1, we want to show, I'm just going to write this out because it's useful to have it. We want to show A is a subset of B, so what we're really showing is X intersect Y, that part in parentheses, union Z equals, and then the B set, which is, we switch over the parentheses to the Y union Z. Okay, so the way we show, whoops, not equals, we're going to show this subset relationship first. Okay, so the way that we show something's a subset of something else, we need to assume let little a be an element of, and then the first set here, the one that's going to be the subset. So let little a be in X intersect Y union Z. And then when we work this whole thing out, the goal is to end up with ... Eventually A is in the thing on the left. Or sorry, the right. X intersect the quantity Y union Z. Okay. The quantity is really the set, right? Okay. So let's break down this one that we have over on the left here. So if A is an element of X intersect Y union Z, then A is going to be an element of, and I'll break this down, it's really right now 2 sets with a union in between them. The first one is X intersect Y, and then the union is the same if we switch it out as or A is in Z. So, and the reason I'm allowed to do that, remember, is definition of unions. Basically, union says element is in one or element is in the other. Okay, so now let's break down the X intersect Y right there. So then that's going to be A is in X and A is in Y, or A is in Z. And that's the definition of the intersection. Okay. Now this one right here is, we can go to our tautology chart that we have, and this one is in a certain form. If I actually flip it around a little bit, it's easier to see which form it's in. So I'm going to write it like this: A is in Z, or A is in X, and A is in Y. I think that one's probably in there somewhere. If, you know, P and Q turns into Q and P, something like that. But I'm not worried about that one. To me, A or B means the same thing as B or A. So I'm not going to worry about switching those back and forth. Over here, I'll write A or B is the same thing as B or A. I'm not worried about whether or not you know why that's true. You can prove that in one step, essentially, with a truth table, in 1 minute with a truth table. So this right here, don't worry about giving me a reason for that. On a test, you can just leave that blank, or you could, you know, I'm going to write duh. right there. All right, now this one is a lot like, it's in the form 1K, theorem 1K, which says this. Theorem 1K says, if you have something in the form P or Q and R, then that is the same thing logically as P or Q and P or R. Okay. So if I apply that to R statements, where this one's P, this one's Q, this one's R, then what I'm going to get is A is in Z, or A is in X, and A is in Z, or A is in Y. Okay, and that's using theorem 1K, or tautology 1K, if you want to think of it that way. Okay, well, if A is in Z, this first part right here, then that means A is in X, because we assumed Z is a subset of X. So the only thing I'm going to do in this step is turn this into then A is in X, and then I'm going to leave everything else the same. Or A is in X, and A is in Z, or A is in Y. And this is because of definition of subset. We assume the subset relationship right off the bat. Okay, well, A is an X or A is an X. That's basically just saying, well, then A is in X. Okay, because I'm really saying the same thing twice. That doesn't add anything new. So A is an X or A is an X. There we go. And A is in Z or A is in Y, I can condense into A is in Z union Y. So really this part right here, from the X or X to just X, that to me is another duh statement. I'm not really worried about that one. The real one that you're using here, so this part right here, I'm going to write duh again, because I don't want to bother with coming up with reasons why the obvious is true. But over on the other side, we're using the definition of union. Okay, so now I've got an and in between A being in the first set and A being in the second set. So I can combine these guys into A is an element of X intersect Z union Y, and that's using the definition of intersection. And now if you look at this, we've actually done what we needed to do. We showed that if A is in this set, which is what we started with, then A is in that set, which is what we ended with. And so now I can write a quick statement. Therefore, X intersect Y union Z is a subset of X intersect Y union Z, like that. So I've done part one. That's good. Okay, so part two. Oh, and this is definition of subset. So part one's done. Part two, I need to do the opposite relationship. Basically, I need to do that one. So let's write that out down here. It's going to be a long proof. So now we want to show that the second set, so this one was set B here, is a subset of set A. Okay, so I'm gonna pick some element from the first one. And then I'm gonna break that down a little bit and then eventually try and build it back up to be this side. So therefore we can say A is in X intersect, A is in X, and A is in Y union Z, and that's definition of intersection. And then we can break this down some more. So A is in X, and A is in Y, or A is in Z. That's definition of union. And so then this one is kind of like the 1K that was up here. there's one that's 1L. And this is a different type of distribution. This one says if I have P and Q or R, then instead of distributing an OR like we did up here, the OR goes to both the Q and the R. This one, the AND goes to the Q and the R with an OR in between. So this would be P and Q, or P, whoops, and R. And let me make sure that's 1L. Yeah, that's how 1L is phrased with those letters. Okay, so 1L, if I apply those over here, where this is my P, this is my Q, this is my R, then I'm going to end up with A as in X and A as in Y, or A as in X and A as in Z. And so that's definition. Oh no, sorry, that's theorem 1L, or tautology 1L. Okay, so let's see now. Here's a tricky one. I'm almost to where I want to be because I can turn this one into A as in X intersect Y, which is good because that's what I want right here. And then I need a union Z. This will turn into the union. This part doesn't turn into the Z quite yet. So I somehow need to get rid of that X. And the nice thing is, if I know that P and Q are true, then I know Q is true. Or P is true, either one. And that's actually called the law of simplification. And that's 2C in your handout. So then this thing right here is going to turn into A as in X and A as in Y. Or A has to be in Z by the law of simplification 2C. So now I can combine some stuff. This means A is going to be in X intersect Y, or A is going to be in Z. And I'm using definition of intersection. And then I can say that A is going to be in X intersect Y union Z by definition of union. And so then I can say I've done what I needed to do, so I've shown what I'm hoping to show up here. If A was in this side, then A is in that side, so therefore I get a subset relationship here. So I'll rewrite that line, except now it's a therefore instead of a show. Definition of subset. Subset. And what I'll do here is I will call this star 1, and this one star 2, and by star 1 and star 2, we know that the first set is really going to be equal to the second set in this case. Oh, I guess I should flip these because that's how it was originally written. This one came first, and this one typically came second in the original. And that's definition of set equality. The way you prove it is you prove the first one's a subset of the second one's a subset of the first. And there we go. That's how it works. Kind of a long proof there. I have no idea how many steps we did, but gives you a little taste of how annoying these can kind of be. Because really what you had to do in every case here was you had to break it all the way down into elements in individual sets and then sort of build them back up again. And in some cases we needed to do sort of random things like this right here, where you actually throw away something because if A and B are true, then either one of them by themselves are true. Okay, hope that helps. And yep, good luck with the rest of the handout.